Nice to meet you, everyone. I am Tomohiro Oishi, working in the Department of Physics, University of Zagreb, Croatia, as a postdoctoral fellow. The title of my talk today is Systematic Evaluation of Magnetic Dipole Excitation based on Relativistic Energy Density Functional Theory. My collaborators include the Professor Niels Bahr and Dr. Goran Krusic. Before my presentation, please let me display this one panel to make an acknowledgement. Our target is the magnetic dipole excitation of even nuclei. Our approach is based on the relativistic energy density functional theory. For practical calculations, we utilize the relativistic self-consistent Hartree-Bogoliubov calculation and QRPA. Our purpose here is to clarify how the magnetic dipole excitation depends on the so-called residual interactions. And here, the residual interactions include pseudo-vector coupling and pairing correlation in this talk. Briefly mentioning our conclusions, first, the sensitivity of M1 excitation to these residual interactions is clarified. Also, the experimental data on the M1 excitation can benefit us to improve the REDF theory. Energy density functional theory. The nuclear EDF theory has been utilized as one tool to calculate the nuclear properties widely in the nuclear chart. And for those two versions, that is non-relativistic and relativistic versions, the former option includes the Skarn and Goni, whereas the later option includes the relativistic meson exchange and point coupling models. For the implementations, the ground states has been calculated by using the self-consistent EDF mean field calculation. The famous example is the Hartree-Bogoliubov. On the other side, for dynamical properties like collective excitations, the quasi-particle random phase approximation has been utilized, or more generally, time-dependent EDF theory has been studied. Why we choose the relativistic version of the EDF theory? So this theory is an effective field theory including nucleons, mesons, and their couplings. And here I briefly summarize the motivations to choose the relativistic EDF framework. Okay, many points are listed here, but I emphasize the final point, that is spin-orbit splitting. And this is one fundamental feature of atomic nuclei, and this spin-orbit splitting can be naturally concluded from the Dirac formalism of relativistic EDF theory. And this ability is indeed essential to investigate the magnetic dipole excitation. For the other points listed here, if you are interested in, please also see the references as I listed here. Let me remind you one basic thing of M1 transition. Here, the matrix elements of the M1 transition is given, and from this formalism, one can see that the M1 transition happens mainly for the spin-orbit splitting levels. On the other side, since the REDF theory naturally concludes the spin-orbit splitting, that can be a natural option to investigate the M1 excitation. In this study, we employ the point coupling relativistic Lagrangian. And for this Lagrangian, we use the DDPC1 set of parameters in the following. For details, please see these references. Okay, so I go to the first topic, relativistic QRPA for M1. For details, please also see our recent publications listed here. As I told, we utilize the point coupling REDF Lagrangian, and its parameters are given by the DDPC1 set of parameters. Also, for the particle-particle channel, we use the Goni pairing interaction. Then, for the M1 excited states, the relativistic QRPA is employed. In this QRPA for the M1 excited states, we additionally consider the isovector pseudovector coupling as the residual interaction. Note that this isovector pseudovector interaction is originally from the one-pion exchange effect. For details, please also see these references. This is one of our results, that is the M1 excitation strength of the calcium-48 nucleus. And here, because of the doubly magic nucleus, pairing vanishes anyway. So the effect of the isovector pseudovector residual interaction is purely seen. From this figure, one can notice that the isovector pseudovector interaction noticeably affects the M1 excitation energy. Also, please note that in the ground state, that is 0+ solutions, in contrast, the isovector pseudovector interaction does not make a finite effect. This is the systematic calculations for calcium isotopes. In the left panel, I show you the calculated BM1 strength. From this figure, one can see that for calcium nuclei, their M1 strengths have 1 or 2 peak distributions. And by analyzing the QRPA transition components, we found that each peak can be attributed to their spin-orbit splitting shifts, that is F7 halves to F5 halves, or P3 halves to P1 half, or D5 halves to D3 half transitions. Note that, okay, the M1 transition is mainly attributed to the spin-orbit splitting levels, but their excitation energies cannot coincide with the spin-orbit splitting gap because of the residual interactions. Next, I move to the second topic, that is the sensitivity of M1 to the nuclear pairing modes. Our original interest in this part is whether the spin singlet or spin triplet pairing mode is dominant or not inside nuclei. We will show you that by studying the M1 response, it may resolve this pairing mode problem. We investigate the M1 response of open shell nuclei using the Goni pairing interaction. For this pairing interaction, two types of the Goni central force is employed, that is D1S and S1P. In the left panel, I show you the figures of the actual potential curves of D1S and S1P potentials. From this potential curve, one can see that D1S interaction mainly supports the S0 pairing, whereas the S1P pairing mainly invokes the spin triplet pairing by its strong attraction in the S1 channel. However, from the relativistic Hartree-Bogoliubov calculations using this D1S and S1P, we found that for the ground state solutions, these pairing models show no difference indeed. In the right panel, I show you the plots of the two neutron separation energies as well as the total binding energies. And as shown here, there is no difference between the D1S and S1P results for these ground state properties. However, for the M1 excitations, the D1S and S1P predict the different results. In the left panel, I show you their M1 excitation strengths, and here the DDPC1 is used for the particle Hall, whereas the Goni pairing is used for the particle-particle channel. On the other side, in the right panels, I also show you their summations of the M1 strengths. Here, M0 in the top panel indicates the non-energy weighted summations, whereas the M1 value plotted in the bottom panel indicates the energy weighted BM1 summations. One can clearly see that these two pairing models predict different results, namely M1 excitation is really sensitive to the coupled spin of nuclear pairing. From the right panel, one can see that if the spin triplet pairing is dominant, the M1 summations can be enhanced. Why that happens? Indeed, there is an essential link between the M1 summation and the pairing mode inside the nuclei. Because of the problem of time limitation, I skip the detailed explanations, but if you are interested in, please see our paper published in the last year. Then I show you the comparison of our results with experimental data. In the left panel, I plot the REDF-QRPA results for these three open shell nuclei. For these three open shell nuclei, there is also a set of experimental data available taken from this reference by Sober et al. Then, by comparing our results with experimental data, we can see that the spin singlet pairing looks as the better option to qualitatively reproduce the experimental M1 distribution, which is really fragmented. On the other side, spin triplet pairing picture has not been validated in our results. So, from the systematic investigation of magnetic dipole, it can provide an evidence of the Cooper pairing mode inside the nuclei. Finally, I also briefly introduce our new results for thin isotopes. Recently, the proton inelastic scattering has been utilized to obtain the magnetic dipole experimental data. These new data can be a good reference to examine and improve the REDF framework. Here I show you our new results for thin isotopes. For thin isotopes, recently, the proton inelastic scattering provided a novel set of experimental data, and we compare it with our results. From this comparison, we found that the quenching of 0.8 to 0.9 is necessary to reproduce the total summation of experimental BM1 strengths. Actually, this is not bad. For experimental M1 distribution, however, it's really broad, whereas our result is based on the narrow resonance assumption. So, further investigations are in process now. Summary of the talk. The relativistic Hartree-Bogoliubov and QRPA calculation is applied to the magnetic dipole excitations. Then we obtain these conclusions as I told you. For future works, we are working for neutron-rich and proton-rich and also deformed nuclei now. Also, the improvement of the REDF parameters is an important task. For this purpose, the experimental data on the M1 and also the other relevant processes may be a suitable reference. Thank you very much for your attention.